The Knight's Tour Problem, a Geometric Approach. Introduction to the method, developing new solutions by modifying known solutions. Copyright 2019-2024 by Jamie R. Gutierrez Salazar, at Jaragusa on X. Methodology Overview. On an 8x8 board, there are 76 geometric configurations through which a known solution can be modified to create new solutions, new bisections or new trisections, according to the geometry of the modified solution. Such configurations are formed by the connecting points through which the connections can be changed to modify a solution, which include 13 squares tilted to the left and 13 tilted to the right, 13 rhombuses tilted to the left and 13 tilted to the right, 12 vertical rhombuses and 12 horizontal rhombuses. To do this, it is only necessary to identify the eventual coincidences between the geometry of the solution that is being modified and the geometry of each of the 76 configurations mentioned above. To see the complete methodology, visit the blog https://kt-by-jagusa.blogspot.com. 1. Selecting a known solution. Numerous solutions, developed in recent years, are available on the web, thanks to the computational implementation of some of the trial-and-error methods. The compilation made by G.P. Jealous, along with the solutions of his authorship, are also options for known solutions. Its reference is https://www.mayhematics.com/ktn/htm. 2. Generating its graphic description. In order to be able to modify the graphic description of the solution under analysis, you can draw it by using an application like MS Excel. We will analyze a solution dated 1780 by the French scientific Mr. Gaspard Monge. 3. Generating its numeric description. In order to generate the numeric description of the solution under analysis, you only have to select a starting cell, select a wandering direction to visit each cell, and assign a sequence number to every visited cell of the board. 4. Identifying a geometric coincidence. As can be seen on the diagram, there's a first geometric coincidence between the analyzed solution and the left-tilted square, with configuration CL04. See Appendix 1. So, these are the connecting spots we should modify in order to obtain a new trajectory. 5. Comparing the coincidence with the numeric description. As can be seen on the numeric description, the segments corresponding to the vertex numbers on configuration CL04 grow in the same direction on each square. This indicates a new solution would be obtained. 6a. Generating the arrow diagram. By applying the vertex numbering rule, we can obtain the numeric description of the new solution, and the vertex distribution allows us to identify algorithm B, A, B, as the one to be applied. Details on algorithm B, A, B, defining the new numeric description as a function of the known one, in Appendix 2. 6b. Applying the vertex numbering rule. The new vertex numbers are obtained by keeping the first, fourth, fifth, and eighth in ascending order of numeric magnitude, without change, and by exchanging the numbers on each of the other pairs. As can be seen, 2, 32, 54 and 64 are kept, and 23 is exchanged with 63, while 31 is exchanged with 55. 7. Generating the tested solutions family tree. By repeating steps 4 to 6b, we can produce the other outcomes of the tested solution. In terms of the new solutions, bisections, or trisections, we can produce with the known solution, by modifying it with the other geometrically coincident configurations we might have found. On this case, 17 new trajectories could be found. Appendix 1. Developing configurations. In order to modify a known solution, you have to find the geometric coincidences between the graphic description of the solution and the configurations of the board size being used. The configurations are all the squares and diamonds you can draw on a board. There are 76 of them on an 8x8 board. Here's an example on how to find the left tilted square configuration CLXX. More details on my blog. https://kp-by-jagusa.blogspot.com. By shifting the top square, one cell to the right, and the bottom cell, one cell to the left, we can see that there are 5 connection positions available, CL01 to CN to CL05. By moving the top square position down one cell, and the bottom square up one cell, we can see that there are 5 additional available connection positions, CL06 to CL10. Finally, repeating the previous procedure are 3 additional connection positions available, CL11 to CL13, for a total of 13 left-tilted square configurations. Appendix 2, Algorithm B, B. If we refer to the upper configuration half as vertices A, and to the lower half as vertices B, we can see the vertex number disposition in the arrow diagram could be referred to as B, B. This configuration disposition is related to case algorithm 1C, where the following numeric conditions, for all the vertices, apply. More details on my blog, https://ktp-by-jagusa.blogspot.com. Algorithm for case 1C, B, B. It applies whenever vertex B, minimum, is lower than vertex A, maximum, which is lower than vertex B, maximum. Then, Mj equals Nj, for every Nj within a set going from 1 to vertex B, minimum. And, Mj equals Sm minus Nj, for every Nj within a set going from vertex B, minimum, plus 1, to vertex A, minimum, with Sm equals vertex B, minimum, plus 1, plus, vertex B, maximum, minus 1. And, Mj equals Nj, for every Nj within a set going from, vertex, A, minimum, plus 1, to vertex A, maximum, minus 1. And, Mj equals Sm minus Nj, for every Nj within a set going from, vertex A, maximum, to vertex B, maximum, minus 1, with Sm equals vertex B, maximum, minus 1, plus, vertex B, minimum, plus 1. And finally, Mj equals Nj, for every Nj within a set going from vertex B, maximum, to n, square. With n square, being the total amount of cells for the board size being used. On our next videos, we will present and explain the other 6 algorithms needed to solve the 9th TOR problem.